Welcome back to the lecture series. In this lecture, we'll be discussing about the structures of coupling structures, techniques, and whereas in the previous lecture I have shown you the different what are the different types of coupling techniques can be used for enhancing the performance of antenna. So first technique will be go for the defected ground structure, but defected ground plane is like we are going to defect the ground plane of the patch antenna. So I'll show you the basic microstrip patch antenna of designing thing, and here you can see the basic patch antenna where this is the ground plane, and here we have printed the patch on the top of the substrate, and here you can see this in the 3D view and a perspective side view where you can see this is a ground plane and here is a uh, patch antenna, and we have feeded using the coaxial feed, and we use there is a design equation to calculate the frequency, the resonant frequency like f naught with the speed of light c divided by 2w root of epsilon r plus 1 by 2 where c is the velocity of light, and next is the width of the patch. So the width of the patch is calculated by using the same like after calculating the resonant frequency we use the c divided by 2 into f naught of permittivity plus 1 by 2. This permittivity is like based on the substrate permittivity. So here I have used the f of 4 substrate. So based on this we calculate the effective permittivity. When we calculate this effectivity permittivity and del L, well we can use for calculating the length of the patch antenna, and length of the ground plane is calculated based on the height of the substrate plus length of the patch, which is total ground plane of length and width. And now I'll show you the design procedure of the DGS. So here I have used the fin DGS, and how I arrived the shape is like say same thing, like we have the basic shape of dumbbell. So from this dumbbell slightly I have moved this dumbbell in the form of shaped in the inverted L, we can call it as an two inverted L shape. From this again I have done this with the small inverted L type of shapes. For this I have done the experimental analysis using the transmission line, by using the transmission line. So this will act like a filter thing. So based on this I have done the equivalent circuit parameter analysis and design equation to calculate the capacitor and the inductor, and then coupling coefficient is calculated based on the k, that is of the difference between the frequency. And here is there is a dimension of fin digits is calculated using L naught, LC and C naught. So these are the basically a derived parameters of fin DGS. And next is like what I did is like we have placed the fin DGS like defected ground structure in the backside of the uh, uh, substrate. Like so here what I did is I have disturbed only the in a non-radiating, so we can call it as an like wherever I have feeded this side we say as in a radiating side of the patch. So always the feeding side we say as in radiating side, whichever is a feeding is not there, that we called as a non-radiating side. So what I did is I have not disturbed on the radiating side, so wherever the non-radiating whichever the field is has been escaped, so that in that field I have disturbed the non-radiating side of the patch antenna. So this what I did is I placed near the non-radiating side of the patch antenna in the ground plane. So by placing this using this gap analysis, I did an gap analysis. So with this I have arrived the what will be the gap between this. So all these dimensions have been as a calculated dimension. So here what, so this length and width is calculated based on the length and width of the patch and then gap between these two. So with this, we have empirically derived the length and width of the defected ground structure. So with this, and I have done the equivalent circuit model of fin edges, like how many number of fins, like this entire area will be we called as an coupling. So for this coupling, we have this, there is a gap between these two, we call as coupling. So this coupling coefficient should be calculated to get coupled with this DGS and then patch, I mean back side of the patch, non-radiating side. So this coupling, I mean ratio is an important thing. So which I have been calculated by using the impedance, input impedance and the load impedance, which is like we can say essence slot impedance and microstrip patch impedance. With that input admittance have been calculated, and with this I have calculated the input capacitance and C naught and inductance by using the same formula. This is 1 by f4 pi f naught square and C. And here you can see what the result has been arrived, like we have seen the no there is a no disturbance in the reflection coefficient, like where the even after no DJs also it is resonating at the same 3.25, and after same 3.3 nearest to 3.25 only it is also resonating. The big S11 is, and S1 is also, there is a good reflection coefficient of minus 30 dB. So both the thing is like we have done the simulation also, measured parameters also. All the parameters has been matched. So I have this is a prototype of the single element fin DGS with I mean a microstrip patch, with the DGS structure. And here you can see the current distribution, and initially you can see there is a large amount of current distribution near the patch of no DGS. When there is, we have placed the DGS, the most of the non-radiating fields, I mean most of the fields whichever is the highly concentrated near the non-radiating side of the patch antenna, it is observed. And why I have done this folded in folded out DGS is like I got the same result. So what I did is I maintained as one thing. So one folded in and folded out DGS. So both are same. So I maintained, I have taken the one structure for the analysis thing. So here what is the gain we have obtained is like for no DGS we have obtained up to the 5.4 dB, and with folded in DGS is almost of same. So based on this gain is also I have got the good gain at 7 dB. So this has been fixed, and here you can see the normalized gain pattern. So and the analysis is like we use this I mean technique to reduce the cross polarization. So when we reduce the cross polarization, obviously that the gain will be get increased. So that is the reason I have we designed the defected ground structure. So this is a one of the coupling technique, like when we suppress the cross polarization, which it will enhance the gain of the patch antenna. Thanks for watching. In next lecture we'll be discussing about other techniques. Thank you.